Hello, okay, this is part 2 of 2 videos on projections of vectors. Okay, so make sure you've watched the first one before you watch this one. Last time around we relied on this diagram here when we were talking about scalar projection. We're going to go a step beyond that now. I suppose it's beyond that. Yes, it is. To vector resolutes or vector projections, but we are going to use the diagram to help us along there. Last time around we looked at OA, line OA it was, but now because we're looking for vector resolutes, we are considering OA, but we're considering vector OA, which it looks like this, with the directed arrow on the top. Let me just get a bit more thickness on that. There you go, a bit more heft there. And so because we've got a vector, we need a direction, so I'm putting that there. So OA, vector OA from line OA. So this stems from what we saw in the previous video. The scalar resolute of B on A was derived last time around. You can see that there. Okay, so B on A, and our most useful result is that there. So for vector OA, the vector resolute or a vector projection of B on A, that projection is given by the following. Now last time with the scalar resolute we got to this, but we also have for the vector resolute a unit vector A dot B by, and that'll be a scalar quantity, that then multiply that by vector A, or unit vector A I should say. So it's like that's what we had for the scalar resolute, times it by its unit vector, and of course unit vector's job is to provide direction and not mess around with the magnitude in any way, and that's how it works there. Now in particular this result is called the vector projection, or the vector resolute of B parallel to A. So B parallel to A. So in other words, we can call it this. Now this is not 1, 1 or 11. That is the parallel symbol, okay? So don't get that confused. Make sure you note that. So it's equal to what we just wrote before. Okay, dot product to give us the scalar, and times by the unit vector. Okay, so that is the vector projection of B parallel to A, or the resolute. Let's take a look back at the diagram now. So because it's B parallel to A, we can call this part here the same thing. Okay, so it's parallel to A, so there we have the parallel symbols there. So it's the resolute of B parallel to A, and it's this same vector OA all the way along. Now there are actually two resolutes. We've got one of them there, okay, the parallel one, parallel to A in the same direction as A. The other one is this one here. Now it is perpendicular, so it has the perpendicular symbol there. Can you see it? I hope you can see it. Now please note that only one of those is called a projection. So this one, this one here, the one caused by the shadow of the flashlight that you saw, or the torch that you saw on the first video, that one there is a projection. this one here is a resolute, and this one is a resolute as well. But only the parallel one is a projection. Okay, this one here is not known as a projection, but it is a resolute. Okay, it's a resolute that is perpendicular to A. This one here could be called the parallel resolute. And this one can be called the perpendicular resolute. There we go. So nomenclature. Now let's look back at the diagram yet again. We've got vector addition or vector subtraction, whatever you want to say, is apparent there. So now we can see that vector B is the perpendicular resolute plus the parallel resolute. So we can do a rearrangement, and there's a reason for doing this, you'll see in just a minute. So vector B minus the parallel resolute. Now we're going to use that, so that's not come out too well, but let me fix that. Alright, it's a little bit better. So just rearranging that, so using vector subtraction or vector addition. So the point of this is that we need to calculate this one first, okay, the parallel resolute, and then from that we can calculate the perpendicular one, because we know B, and once we determine the parallel resolute we can determine the perpendicular resolute. So you won't find the perpendicular resolute on too many formula sheets because really you're just using vector addition. Once you know B because it's given in the task, you can work out the parallel resolute, and then you can work out from there using vector subtraction the perpendicular resolute. We can say the vector projection of vector B on vector A, or instead of on, in the direction of A, we can write it as such, okay, and we can call it a vector projection, remember, because the perpendicular one doesn't get called a projection. So when we say projection, we know we mean this one here, the parallel one. And of course we've already established earlier on this, and it has its equivalencies as discussed in the previous video. These are all the variations which are all equal to each other. We can easily verify this if we just know a little bit about basic vectors. Okay, so writing these in, and you may very well find these on formula sheets. Just got to know how to use them. Yeah, so that's that one, and we've got the vector resolute of B perpendicular to A is given by remember, it's that vector subtraction, so we just take off the one above there, as we can see. So we've got vector B, take the unit vector A, B, unit vector of A. Okay, so that's the vector resolute perpendicular to A. Let's do a quick example to finish off, and we'll do one of each in this example: a scalar resolute, a vector projection, and a vector resolute that's perpendicular. Okay, so given that A is negative 2i plus 3j and vector B is 4i plus 2j, so note those. We have to find three things. The first thing So the scalar resolute of B on A. Okay, let's find the required magnitude first, and then we can find the required unit vector. Okay, so it's, the magnitude is root 13, and it's fairly easy to generate the unit vector of A as given there. Alright, and so we look at our formula, and for a scalar, remember we're doing the scalar resolute here, so don't put the vector equation in there, and we have multiplying that together because it is a dot in a sense of the dot product, that is. But be careful if you use the word multiply when you're dealing with vectors, that's for sure. Okay, so we've got everything written down there, and let's compute that. So we've got negative 8 over root 13, and we've got 6 over root 13, so that comes out as negative 2 over root 13. Okay, second thing we've got to find is the vector resolute. Okay, and that's parallel to A. Parallel to vector A, and let's go, that's a step, just one step beyond what we just did, so this should be pretty quick. And sub those things in, we've got 4 over 13, negative that is. Oh no, it's two negatives, it makes positive. Alright. Positive 4 over root over 13, not root 13. So 4/13 I minus 6/13 j. Okay, the third thing, vector resolute perpendicular to A. So this is where we use subtraction. So that's the symbol, and we go B minus the parallel resolute, and we have all those bits of information. Just have to be careful of subtracting negatives and whatnot. And 6j over 13. And we go ahead and subtract that, and we've got to find lowest common multiple. Because we're dealing with fractions there. And there we go. Okay, so 48 on 13i plus 32 on 13j, and that's our vector resolute perpendicular to vector A. I hope that worked for you. Until next time, ciao.